Hi everyone, I'm Andy, and today I'm going to talk to you about a new method, MS1Connect, that uses MS1 scans or intact peptide scans to measure the similarity between pairs of mass spectrometry runs. So let's pretend you're in the following scenario. You have some data set and you're trying to find additional data that's like your own data. So why might you be in this situation? So maybe you run some analyses and you want to validate the results of that. So you need to find additional data that's similar to your own data to validate your results. Maybe you want to augment your data set. And so in performing some joint analyses across multiple data sets, in order to do that, you need to find data sets that are similar to your own. So now the question becomes, where do you find this additional data? And the easy answer is going to online mass spectrometry repositories, such as Private Massive. These repositories have a wealth of data, and what you see here is a plot of the number of data sets that are deposited into Pride each month over a period from 2012 to 2019. And as you can see, there's just a large number, an increasing amount of data being deposited into these data sets and these repositories. So the question now becomes is out of this massive amount of data, how do you actually begin to find data sets that are like your own? How do you find mass spectrometry runs that are like your runs? And more concretely, how do you actually measure the similarity between two pairs of runs? So current methods that measure the similarity between pairs of runs use MS2 scans or peptide fragment spectra. And one of the more common ways to do that is to calculate the Descartes index of completely detected peptides. So if we have two different runs, we can do a database search to get the set of completely detected peptides, and we can calculate the Descartes index of between these two sets. Another method is to calculate the distribution of spectra dot products between two sets of spectra and see the number of spectra above some spectra dot products above some threshold. So in this example here, we have the distribution of spectra dot products between a human data set and against various other species such as E. coli or gorilla. And looking at the purple line, which is comparing human and E. coli and bacteria, you see that there aren't very many pairs of spectra that have a high dot product. Whereas when you compare humans and gorilla, which is this orange line, you see there's a fair number of spectra that are similar enough to each other. So one of the drawbacks of these methods is that they all focus our MS2 data on these MS2 scans. And the problem is that MS2 scans are not always comparable to each other. There's many ways to acquire proteomics data sets. Two of the more common ways include data-dependent acquisition and data-independent acquisition, DIA and DDA. In DIA and DDA, you actually collect intact peptide scans the same way, MS1 scans in the same way, but you actually acquire MS2 scans slightly differently. MS2 scans in DDA, all of these peaks, all these peptide fragment peaks, all result from a single peptide. Whereas in DIA, there's multiple peptide fragments found in here. So these are the fragmentation events of multiple different peptides. So in addition, measuring the similarity between a pair of proteomic runs is just generally hard. So what you have here is the same sample run two different times. And I'm just showing two of these runs, where the x-axis is time, the y-axis is max charge ratio, and the color is intensity of peptide features. You can already notice that the amount of time collected, even though these are the same samples and on the same instrument, are collected for different amounts of time. Another thing you notice is that peptides are coming out at different times. You see that in the top run, these two peptides are coming out around minute 95, whereas in the bottom run, these two peptides are coming out around minute 70. You can also see that mass spectrometry runs have different numbers of peaks. You can see there's a fair number of peaks in this bottom run that just are not existed in this top run. And finally, different runs can have different intensities. Looking at the top run, you see these three features within the white circle have middling intensity, but if you look at their, compared to the bottom run, you see that these features have much higher intensity. So today I'm going to talk about MS1Connect and how we measure the similarity between the pair of runs and how we overcome the issue of MS2 spectra. We overcome this issue by just only looking at MS1 information. And MS1 scans are always collected in the same way, so we can actually compare DDA, DIA, and target analyses all together at the same exact time. So as part of that, I'm going to talk about how we represent a pair of mass spectrometry runs as a bipartite graph. Then we're going to talk about how we represent mass spectrometry run similarity as a maximum bipartite graph matching problem, how we select the matching, how we score matching, and then I'm going to show some results showing that we successfully measured the scores of the mass similarity between two runs. So how do we represent a mass spectrometry run, a singular run? And so what we do is we represent a single run as a bag of MS1 features. So we take all of our MS1 scans, we're going to send it through feature detection to get specifically pipe with MS to get a set of features, MS1 features. Each feature has 4 values, M over Z, time, charge, and intensity. We represent a pair mass spectrometry run as a bipartite graph. Bipartite graph has 2 sets of disjoint nodes and edges that link nodes in the 2 disjoint sets. In our setting, we have the set of MS1 features from one run and the set of MS1 features from the second run. And edges are going to link MS1 features that have the same exact charge and similar M over Z. This is schematic shown on the right to give you a sense of what the real data looks like. This is 3 views of the bipartite graph formed by 2 different runs, where the gray planes are the boundaries between the 2 runs. The purple lines are the MS1 features from one run, the orange lines are the MS1 features from the second run, and the green lines are the edges linking MS1 features. And we have 3 axes shown in this data: time, mass charge, and intensity. So next, we're going to talk about how we represent mass spectrometry run similarity as a maximum bipartite matching problem. So in a maximum bipartite graph matching problem, we want to choose a subset of edges A that maximizes score S. We want to choose a subset of subset of edges A that's subject to a certain constraint. And the constraint we have is that each of the MS1 features in A could be associated with at most 1 edge. So looking at this schematic here on the right, we see that there's 2 edges here in blue that are both associated with this particular MS1 feature. So as a result of this constraint, we can only choose one of these 2 blue edges whenever we choose a matching. So we have this constraint because we've done MS1 feature detection. As a result, every MS1 feature is associated with a peptide, and we don't expect the same peptide to show up multiple MS1 features. So this is why we have that constraint. So after we choose a subset of edges A, we have to actually score it. So how do we actually score it? So we score it using this MS1Connect projection function, which is a weighted combination of 4 different terms. I'm going to go through this whole equation right now. So we have the score between 2 runs, R1 and R2, of some sort of subset of edges A. The MS1Connect is a weighted combination of 4 terms, and each of these terms are going to be represented by M(i). So we have the weighted combination where lambda I is a hyperparameter, and we normalize each of the 4 terms in order to get an intuitive understanding of the relative importance of each of the terms. This here is just saying that we want to maximize the score. We want to choose a subset that maximizes the score subject to the constraint that we talked about previously. And this here is a value that serves to denormalize the normalization we did previously to make sure that the score is on the correct scale. And so next, I'm going to talk about each of the 4 terms individually and how each of the terms individually measure a different aspect of proteomic run similarity. So the first term, M1, counts the number of edges found in the solution. And it's going to favor solutions that contain a large number of edges. So we have here on a schematic on the right-hand side, we see that M1 is going to choose the 4 edges in blue. It's not going to choose this edge in gray, because if it chooses that edges in gray, it cannot choose these 2 blue edges. M2 sums the product of the 2 intensities associated with each edge. And so in this particular case, it's actually going to choose this with 1 blue edge instead of these 2 gray edges. And to give an example, I'll show you why. We have, let's say these are the intensities associated with each of the MS1 features. So the scores of the 2 gray edges are going to be 50 and 10. So by summing them together, we get a score of 60. But if you look at the score of the blue edge, we see that's 100. And since 100 is greater than 60, M2 is going to favor this blue edge instead of a combination of these 2 gray edges. M3 looks at the negative exponent of the difference in retention time. So it's going to choose edges that have small retention time shifts between the MS1 features that is linking. Where alpha is a hyperparameter, indicates how problematic a large retention time is. And so as a result of that, M3 is going to choose this edge because the two MS1 features that it's linking have a smaller difference in retention time compared to this gray edge here. And finally, M4. So M1 through M3 up until now that have been working on individual edges. M4 instead works on pairs of edges. And M4 is going to favor solutions that contain many similar pairs of edges. So what do we mean by when we have a similar pair of edges? So just for each pair of edges in solution set A, we're going to boost the score when there's time shifts. So of the two edges are similar. And then we're going to also boost it when the pairs of MS1 features are the same amount of similar retention times. In the next set, I have an intuitive understanding. The thing I want to point out is that we have two alpha parameters, beta and gamma, that also do indicate how problematic a big difference is. So this is the schematic, and in M4 is in M4 will be choosing these three blue edges instead of the singular gray edge, even though the singular gray edge has a smaller retention time difference. And this is just because of that boosting. So we have three blue edges that have similar differences in time shifts, and they all start around the same time. So we're going to boost them up, and these two factors in play kind of indicate that this retention time shift is probably correct. And that's why we want to boost the score. And this makes sense because we don't expect liquid chromatography to be consistent across labs or across experiments. All right, so that was a lot of information. The main takeaway is that MS1Connect's score is a weighted combination of 4 different terms. For each term measures a different aspect of proteomic similarity. 3 of the terms are modular, and 1 term and 4 is supermodular. A modular function is just when the sum is equal to the sum of its parts. So we have 2 sets of items, A and B, and a scoring the function F. F of A and F of A and F of B is equal to the sum of F of A union B. On the other hand, a supermodular function is greater than the sum of its parts. So F of A union B is greater than F of A plus F of B. Okay, next I'm going to show you some results on how MS1Connect scores, evidence that MS1Connect scores can measure the similarity between 2 runs. So the specific task we want to do is species identification. And since we have hyperparameters, we need to do a hyperparameter search. So we have the training and test set. So we have these 9 different species. In these 9 different species, there's up to 5 different projects that we grab data from. And from each project, we grab up to 5 different runs from that project. So there's a wide amount of projects and data sets and issues that are encompassed in this data set. We have training and test data sets, none of the data overlap. And 3 species are shared between the test and trained data set. So we use 2 different metrics when we're trying to see how it does on the species identification task: per query average precision and aggregate average precision. The per query average precision takes the mean of the average precision over all the queries. So giving a set of data, we're going to select 1 to be a query and the remainder to be a repository. And then we can calculate the average precision for the specific query. Since we have a whole number of data sets, we can actually make each individual run a query, and then we can actually calculate the average precision for each of these queries, and then take the mean of both those average queries, average precisions, and that gives us the per query average precision. The aggregate average precision actually just only considers this upper triangle of scores, and it's going to sort these scores shown in pink, and we create one individual precision recall curve where true positive occurs when the pair runs to the same meta label. All right, and so this is some quantitative results showing that MS1Connect scores consistently predict species label per run and outperforms our baselines. Our baselines here are based off of binning MS1 features and calculating the scale of products. The 2 bolded values in each column are the second best performing method out of each column. So the first thing to note is that MS1Connect outperforms all of the baselines for both the data sets across both performance metrics. In addition, we see that there's 2 methods, this first line and the second version of MS1Connect, that both incorporate M4, which remember is the supermodular version. Both of those outperform the modular versions. So this just indicates that the supermodularity, this M4 term, is really important for getting good performance. This is a heat map of the MS1Connect scores for the training data set. We have here the gray lines delineate between projects, the solid white lines delineate between species. We have a phylogeny. And we see the strong, and the colors are MS1Connect scores. We see a strong diagonal component showing that runs from the same experiment are highly similar to each other. And we also see that runs from the same species also tend to be very similar to each other. In addition, we can see that interspecies relationships are also showing up as MS1Connect scores. So these two species are in the same genus, and you can see that they're also and they're very similar to each other. As another example, we see that humans and mice are pretty similar to each other, and this makes sense in the context of our our data set, because we include bacteria, we have in plants as well. Next, we showed that MS1Connect scores replicate database search results. So we have 16 samples labeled 1A through P, and each of these samples contains 1 to 3 different organisms, which is shown in this table here. Each sample was run 4 times, 3 times in one lab on an LTQO retracted Excel, and a 4th time on a QE in a second laboratory. Same samples, 2 different laboratories. And we can show that we can replicate database search results. So what we can do is we can calculate the Descartes index of the set of completely detected peptides between 2 runs. And that's what's shown in this lower triangle here. In the upper triangle, we have the MS1Connect scores. And you can see that, and then the solid white lines delineate the boundaries between samples. And you can see that the bottom and upper triangle are a pretty good match for each other. One thing to note is that you might see this checkerboard pattern. This checkerboard pattern results from the fact that we have 2 different laboratories involved. We have the first 3 runs are from one lab, and this 4th run is from the second lab. And you can see that our scores are able to replicate these similarities that result from these different laboratories. So today I've talked about MS1Connect, a mass spectrometry run similarity score. I've talked about how MS1Connect represents scoring the similarity of a pairing run as a maximum bipartite graph matching problem. I've shown you how MS1Connect scores are successfully used for species identification and outperform our baselines. And I've also shown you how MS1Connect scores replicate similarities generated from MS2 data. With that, I'd like to thank the people who have helped me on this project, Jeannie Hutchison for Kaiser, and my advisors in graduate school, Jeff Films and Bill Noble. And I'll take any questions. Thank you.